What's good, people? Chilo Chasha here, back with another video. I know I haven't been uploading much lately. Life's been busy with work and other commitments, and honestly, I just haven't felt that motivated. But yeah, that's how it goes sometimes. Good news though, I am back at it now and I'll be uploading more consistently. So if you enjoy civil and geotechnical engineering content or you're just curious about the built environment around you, make sure you like this video and subscribe to the channel. I've got a reaction video for you from a great channel called The Engineering Hub. They make top-notch engineering content, so I highly recommend checking them out. I will leave the link to the original video in the description below. The title of this video is Understanding Why Soyuz Fell, and this one takes a more of a theoretical approach, which is exciting. It's always good to understand from a geotechnical perspective the fundamental principles that shape design decision all the way to construction. So, without further ado, let's dive into the video.
Understanding soil mechanics is crucial for any geotechnical application. Specifically, understanding the capacity or limits of the soil is what enables successful design for foundations or earth-retaining structures. This video will be one of a series of geotechnical videos explaining retaining walls, shallow foundations, and stability of slopes from an engineering point of view. However, before we dive into these geotechnical applications, first we need to understand some basic principles of soil mechanics. Soils, unlike other construction materials such as steel, timber, or concrete, are almost always under compression. But interestingly, soils never fail in compression. All practical soil failures are due to excessive shear stresses. Shear stresses are less intuitive, so let's have a closer look. The shear capacity.
So, yes, subsurface materials like soil and rocks are fundamentally different from other construction materials. So for simplicity, I'll just refer them to as soils from now on. Unlike steel, wood, concrete, or plastics, soil are made up of discrete elements, that is, the mineral particles, organic matter, water, and air voids. And the interaction between these elements determine how soil behaves, making it a complex material to work with, which you will see later in the video.
Of common engineering materials, such as steel, timber, or concrete, is governed by the strength of their molecular bonds, and therefore, usually is fairly high. Soil, on the other hand, is a discontinuous particulate material made up of various size particles. The interlocking of these particles is what gives the soil its resistance to shearing. When the shear stresses along a particular plane or slide surface are large enough to make the particles roll or slide past one another, failure is initiated. In the field, shear failures of a soil mass are usually confined to a narrow zone where rearrangement of the particles occurs. Without these interlocking forces, the material would behave more like a fluid rather than a solid. This condition, where the soil turns into a fluid-like material, does happen sometimes and is known as liquefaction. But it is a specialized case, and we will not worry about it for now.
Soil liquefaction is an interesting phenomenon. As explained in the video, the interlocking of soil particles governs the soil strength and the load-bearing capacity. Now, soil liquefaction is a unique type of failure that mainly affects granular soils like sands and gravels, especially in earthquake-prone areas. Let's say you have a structure built on saturated sand, meaning that the spaces between the soil particles are filled with water, right? When an earthquake strikes, ground vibrations cause soil particles to shift and try to compress the void spaces. Since water is incompressible, it tries to escape, but because this happens so quickly for drainage to occur, pore water pressure suddenly increases, putting all the soil particles in suspension. This reduces shear strength to almost zero, meaning there is no more solid particle interaction, so the ground will behave like a liquid. As you can see in these photos, the buildings collapse, but notice they are still structurally intact.
Besides the interlocking or frictional strength, soils also possess cohesive shear strength. Cohesion, in practical terms, represents the stickiness of the soil, such as in clays, but is usually zero for coarse-grained soils like sands and gravels. What makes things complicated is the fact that the frictional strength of the soil is dependent on the pressure the soil is under. This makes intuitive sense, since if the soil is compressed, the particles get further interlocked and sliding becomes more difficult. On the other hand, submerging the soil underwater has the opposite effect, since the buoyant force from the water helps the particles become partially afloat. In more technical terms, the pressure from the water and friction resistance of the material. In practice, the strength of soils is represented by the Mohr-Column failure criterion. The German engineer Otto Mohr graphically represented the strength of the soil as a line on a graph, with the material's normal stress plotted on the x-axis and the shear stresses on the y-axis. When the soil is loaded, it forms a semicircle on this plot that is known as the Mohr circle. The two ends of the circle represent the normal stresses that the soil is subjected to. An alternative way to look at these stresses is as a confining stress on the low side and an applied stress on the high side. These stresses are also known as the principal stresses of the material. Notice that to keep the circle small and away from touching the failure envelope, we need to increase the confining stress together with the applied stress. In theory, if the soil is well confined, its carrying capacity can be increased indefinitely. Note that every point in the soil mass draws a separate circle on the graph. As the soil continues to get loaded, the circles grow until one or more of them touch the failure line. The point in the soil mass whose Mohr circle touches the failure line first is where the sliding in the soil will occur. This usually happens simultaneously for a whole plane in the material, which initiates a sliding failure. The slope of the failure line is represented by a parameter called the friction angle, which is the single most important strength parameter for a coarse-grained soil. If the friction angle is high, then the soil can resist higher shear stresses.
Now we're getting into the meat and potatoes of this video. Two of the most important soil parameters in foundation design, retaining wall construction, and slope stability analysis are the internal friction angle and the undrained shear strength. They are derived in a similar way but function differently, as I will later explain down in the video. So for granular soils like sand and gravel, gain strength from friction between particles along the shear zone and from the confining pressure. And on the other hand, the cohesive soils like clay and silt rely more on the electrochemical bonds between the particles and what is called particle cohesion. To understand these concepts a little bit better, let's take a closer look at Mohr circles. Back in the late 1800s, Christian Otto Mohr, a German civil engineer, expanded an earlier graphical method for stress representation, and this eventually got developed into a technique we use today. And his work was further refined in the early 20th century by Karl Terzaghi, who is regarded as the father of soil mechanics. And this Mohr circle has revolutionized geotechnical engineering and remains a critical tool to understanding stress states and predicting soil behavior under different stress conditions. One of the most widely used methods for determining soil strength parameters is something that we call a triaxial shear test. A soil sample is enclosed in a rubber membrane inside a triaxial chamber. Then water pressure surrounding the sample is used to simulate the ground confining pressure. For sand samples, increased pressure allows water to drain, increasing particle contact and therefore increasing the shear strength. And these tests are repeated at different confining pressures, and different Morse circles are plotted. You will notice that the higher the confining stress, the larger the Morse circles. If we plot a tangent line to all the circles, forming what we call a failure envelope, and its slope represents the friction angle and its y-intercept represents cohesion. But mostly in granular soils, the cohesion is considered negligible. On the other hand, cohesive soils like clay and silt behave differently from granular soils due to their low permeability and strong interparticular cohesion. When subjected to confining pressure, cohesive soils do not allow rapid drainage, meaning that pore water pressure remains trapped within the soil matrix. This influences the way stress is distributed and how failure occurs. So, unlike granular soils, where increased pressure leads to drainage and enhanced particle contact, cohesive soils retain water, preventing significant changes in their internal structure. As a result, when shear stress is applied, the Morse circles remain roughly the same size across different confining pressures. This is because the soil does not develop additional frictional resistance from particle rearrangement. The failure envelope for cohesive soils is typically horizontal, meaning that cohesion is the dominant strength parameter rather than the frictional resistance. This is known as the undrained shear strength, which is crucial for short-term stability analysis, especially in excavations, embankments, and foundation loading. Over time, however, as the pore water pressure dissipates, cohesive soils, so the clays and the silts, transitions to a drained condition where now effective stress takes over and governs their behavior.
The physical meaning of the friction angle is related to the incline angle at which the soil slips during failure. This is particularly important in the design of retaining walls and shallow foundations, as we will see in the upcoming videos. For someone unfamiliar with yield lines, this may seem overwhelming. The most important takeaway from here is that the parameter called the friction angle is what determines the strength of a soil. The friction angle of a soil is influenced by the soil type, shape of particles, groundwater condition, and void ratio, among other things. So angular, well-graded, compacted soils exhibit high friction angles and make up for the best type of soil to be used as backfill or to build a foundation on. Stay tuned for the upcoming videos where we will be discussing geotechnical applications such as retaining walls and foundations.
So that's it for this video. If you found this interesting, please drop a like and subscribe to the channel. I really appreciate the support. Thanks for watching. I'll see you on the next one.